Before I discuss the Kirov-Argyle paradox and the Stephenson-Maxwell paradox, I need you guys to watch a prerequisite video. It's one by Vsauce. It's called the Banach-Tarski paradox, and it's uh, it's sort of I recommend that you guys take it or watch it so that you guys can understand at least some parts of this video. So the goal of today's video is to show that a set H with an element, with a certain element. The goal today is to show that a set H is the same as itself without a certain subset. And with that, we will prove that femboys are not gay. Yes, this is one lecture of many lectures that I plan to discuss in a new course called Femboy Theory, which is that theory taught femboys and all that. So you guys should already know about the femboy set because I discussed that in a previous course, which is femboyology, Virology 3A. And but the femboy set that we will define in femboy theory is more of a group. And when we talk about a group is basically a collection of actions we can do on an object. So if we can, let's say we have this marker over here, if we want to rotate it like this, or rotate it like that, or rotate it like this and that, all those actions of rotating this thing we can characterize or denote by letter A or A sub I. A sub 1, dot, 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 and then A sub, or we can use exponential notation and go A sub 1, A squared, dot, 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 A sub n, which denote multiple rotations of one. So this is one rotation, and then A squared is doing the same rotation twice, right? So basically, if we denote A sub I as the rotations we can, or things we can do to this to translate or change its orientation and collect those into a set, that is what is called a group. So a group is a collection or a set of rotations we can do on an object. And that is the primary basis for the femboy set in today's video and in this course. So unlike the previous femboy set that I discussed in femboyology, this femboy set is entirely different as it is in fact a group. So note the femboy set in femboy theory is a group. So this time we denote F to be a group composed of the actions, the null set, H, which is the homosexuality element, the male exclusivity element, and the femininity element. So these are the main things that compose a femboy set or a structure. Since we've endowed this set with a specific purpose and specific elements, we can call this a structure. This is a structure, like how algebraic structures are set wherein we can perform algebras on them, like x, y, z, and the set of all integers. So this over here is a structure, but we're gonna call it just the femboy set. And the first thing, the first thing that's I sort of want to discuss before going to the Kirov-Argyle paradox is theorem number 1. And this theorem states that F is equidecomposable with itself minus the set H, or the set that contains H, or the subset that contains H. And when we say F is equidecomposable with F minus it, when we say the two sets A and B are equidecomposable, then we're saying that when we take A apart, and rearrange it in a certain way, we can get B. And Likewise, if we separate B into countable pieces, we can rearrange them to get A. So therefore, A and B is congruent and the same via equidecomposition. That's why we call it equivalently decomposable. So it's equivalently decomposable. So if we separate this into some minute pieces, we can rearrange them to get B exactly, and that their area or their volume is exactly the same. All right. So using group theory and subset theory, we're gonna prove that F is equidecomposable with itself minus the homosexuality trait, and thus proving that femboys are not gay. So to begin the proof, let R. So let's consider a set that contains H row. Oh my markers are not that well nowadays. Let's denote it via row. Let's denote a set row that contains H and is contained entirely inside F. So rho is a proper subset of F. I say proper subset because rho cannot be the entirety of F. Just some restrictions so that we don't run into some problems. All right. So R let R be an action on rho. So R is an action on rho that maps its elements onto some other thing. So it's sort of it can be thought of as a rotation of rho. So we can think of rho as a circle that's contained inside F with H as the center. R is an action that rotates the circle. It rotates the circle and thus maps H onto a separate point. And that point that H gets mapped to some other point, and then so on and so forth. So the points the points RH R squared H dot 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 R and H are distinct. These points are distinct, or H at the beginning. H R H. So nothing, no action, some action, double action, and then so on and so forth. These guys are distinct. When we say distinct, that means they don't correspond to each other. So this is not equal to this. R to the n is not equal to R to the n minus 1H. So any two actions here on the set H or the center is not the same. That's what we mean by distinct. And they do not correspond to the empty action, which is denoted by epsilon. Not element of, but the empty action. None of these guys results in the empty action. All right. And so now we just simply need to apply R again on this set. So the set H union RH union R squared H union dot dot dot. We just need to apply R onto this set so that we get R squared H, R cubed H, R fourth H dot dot dot. And therefore, from there, you can observe that H is gone. So that means this is the set R acting on P without H. And since it's contained entirely in F, we can say that this is equivalent to this set. So therefore, this is equal to that. And so F is equidecomposable with itself that wherein H is missing. Now that we have discussed that, we just need to apply this logic a little bit further to obtain the Kirov-Argyle paradox. Now, what is the Kirov-Argyle paradox? The Kirov-Argyle paradox is basically we're using a more elaborate form of Theorem 1 to construct Theorem number 2. Theorem number 2. Let n be the sets that are fixed by some non-trivial element by some non-trivial element of F. So when we say non-trivial element, it can be sort of a set of all words. You can say, to be more precise, we can say it's the set of all words on F. So we can say that uh, it's a free group, actually. Free group, the set that contains all the generators within F. So F is composed of what we know to be the null set, M, F, and H. These guys are called generators of the free group on F. And the free group on F is basically the set of these of the possible countable words that are composed of these guys and the reverses. So, right, going back to the rotation analogy, if we do one rotation in another rotation, that is a word. So we apply this and this, doing nothing, and then this, that is a word. Doing this and its reverse is another word. But I must state that we cannot use words wherein we're given the empty word, which means if we rotate it and go back, we get nothing. We cannot backtrack basically when we rotate it. So we can rotate it one way and then rotate it another way, and then we can sort of go the reverse of the original one. That's all right. So the set that contains those possible words or those rotations is basically the free group on F, composed of these guys called generators. And now F is equidecomposable. So N is composed of the things that we want to take away from this set. So we want what we already proved that we can take away H and detach it from F. So here we're gonna prove that M and F are sort of independent of F. And from there, we can say that the femboy, it does not need to be feminine or male, which is a contradiction. So we're basically saying that F is equidecomposable with F not containing N. So F without N. So F without these two elements. We're gonna use these two over here. Maybe even include H. So it's basically F is defined to be this but this is equivalent to itself without M and F. So basically, a femboy does not need to be feminine or male to be a femboy, which is a contradiction with our intuition as to what a femboy is. And so, yeah, here's the proof of theorem 2. All right, we're basically just gonna apply the previous one, but it's a more elaborate one. So let there be a reference point. You have a reference point for actions on F, an element or subset that stays the same, but others are unchanged. Let's use the empty set. Or maybe H, but let's use the empty set. So all the other things around it, like M, F, and H are changed and mapped, but itself doesn't get changed. So it's sort of a rotation, it's the center of the rotation. And so there is a subset that contains the central element of F, but doesn't contain other elements. So it contains this is the central element of F, but it doesn't contain these guys. It runs through this, which is the center, but it doesn't run through these points. So okay, let's go back to the action R and apply it on the set N. So N is composed of F, H, and M. So male exclusivity must be a guy, must be feminine, must be gay, or not. So N contains these three things except the null one, which is our reference point for the mapping or actions. So we just need to, let's apply R on N, on the set N, and it's multiple points. So the things, the actions N, Rn, R squared N, dot dot dot, so on, are disjoint. Now we just, again, like the previous one, we just need to apply R on the set N union Rn union R squared N, dot dot dot, to obtain or to detach N from F. So therefore, F and H are not with N. And so therefore, hence, F is equidecomposable with F without N. So basically, N or the set N is missing because we applied that rotation. And by taking away a part of the circle, and having others fill its spot, it just keeps going on. And so it's as if the point over there or this part that we detached never existed. It's as if we never needed it in the first place. So there we have it, the Kirov-Argyle paradox.